Welcome to Study Loop.
We have an ideal gas that is being added some energy into, it is being added some heat into, and this heat is given the problem. Due to additional heat, the temperature of the gas will change and it will increase. And here we have the initial temperature and the final temperature, and as well we have converted the change in temperature into kelvins, and this is the change, the total change in temperature. So we also know that the work done after the addition of heat is also given in the problem. It is 223 joules, and we need to find the change in internal energy for the part A of this problem. So to do so, we will start from the first law of thermodynamics. The total heat flow of the system is equal to the change in internal energy plus the total work done. From here, we can derive that the change in internal energy is equal to total heat of the system minus the work done by the system or on the system, it depends on the sign. We can then substitute the known values and say that this will be equal to and here we say we know from the problem that Q will be equal to 970 joules and that the work done will be plus 223 joules, so this will be negative 223 joules. From this, we can conclude and evaluate that the change in internal energy will be equal to 747 joules. This is the amount of energy that goes only into the increase of the system's energy as internal energy. For the part B of this problem, we want to calculate gamma. Gamma, let's remind ourselves, it's equal to the ratio of specific heats under constant pressure, Cp. This is for the constant pressure, this is for the constant volume, Cv. So these heat capacities, we need to find some equations that involve these known values, and our known values are the heat exchanged, we know the temperature change, we know the number of moles. So we need to find an equation that involves both heat capacities, or two equations in this case, and solve first for them, and then in the end we will find the ratio and solve for the gamma. So the first equation that is obvious is that Q, the heat, under constant pressure, when the temperature changes under constant pressure, the heat is equal to number of moles times specific heat capacity times the change in temperature. From here, by algebraic transformation, we can move n and delta t to this side and obtain that Cp equals to Q over n delta t. Next, we can simply substitute the known values. So the heat will be 970 joules. Number of moles, 1.75 moles, times temperature change in kelvins. And this equals to, when we put these values into a calculator, we evaluate it at 37 joules per mole Kelvin. Next, we know the specific heat value for the capacity under constant pressure. This is Cp, but now we need to find a specific heat capacity under constant volume, and this can be done from the relationship between the Cv and Cp. the relationship is that Cp equals Cv plus the gas constant. And from here, we derive that Cv equals Cp minus R. We know both. We know R and we know Cp. We evaluated it. So Cv will be equal to 37 joules per mole Kelvin minus 8.314 also joules per mole Kelvin. Finally, Cv equals 26.78 joules per mole Kelvin. And now we need to evaluate the ratio, which is the final answer for this part of the problem. So the ratio will be gamma equals Cp over Cv. Substituting the known values, this is a dimensionless constant, so it will be just numerical values, 37 all over 28.68, and dividing this number, we obtain that gamma equals 1.3, and it is unitless and it is always larger than 1 as a number. So here we have solved both parts of the problem. I hope you find this helpful, and I hope to see you in another lesson.